Okay, let's talk about a problem that I'm sure every single one of us in the AI space has run into. It's that feeling of downloading a huge new language model, you hit run, and you just cross your fingers hoping it actually fits on your hardware. We're going to replace that hope with certainty.
Yeah, this screen. We've all been there. You wait forever for a download to finish, you're excited to try out this new model, and then bam, that dreaded out-of-memory error. It's a total project killer. But the good news is you never have to guess about this stuff again.
You see, the secret to figuring out exactly how much VRAM you're going to need isn't some crazy, complicated formula you have to look up online. Nope, it's actually right there, hidden in plain sight, encoded directly inside the model file you just downloaded. You just have to know how to read the label.
And the key that unlocks all this information for us is a file format called GGUF. Once you get what this is, you'll have complete control over your local AI setup.
So, what is it? Well, GGUF stands for GPT Generated Unified Format. At its core, it's a really smart, compact file that does two things at once. It stores the model's brain, its neural network weights, and it also packs in a ton of metadata that describes exactly how that brain is wired.
Probably the best way to picture a GGUF file is to think of it like a shipping container. Inside, you've got all the important cargo, which is the model itself. But crucially, attached right to the outside of that container is a detailed manifest. And this manifest tells you everything you need to know about the contents without you ever having to crack it open. And that's exactly why GGUF is such a game changer. Because that manifest is bundled right in, our tools can read all that metadata super efficiently without having to load the entire, multi-gigabyte model into memory first. It's stable, it works everywhere, and it tells us the whole story. The number of layers, the vocabulary size, all of it. All right, so now we know where to look inside the GGUF file. So let's talk about what we're actually looking for. When it comes down to it, VRAM usage is really driven by two main things. First up, the most obvious one, the model's size. This is the literal size of the neural network's weights. It's the biggest piece of the puzzle by far, and its size is totally fixed. If a model file is 17 gigabytes, it's always going to take up at least 17 gigabytes of VRAM. That's our baseline.
But then there's this second piece, and this is the interesting one, the KV cache. The easiest way to think about this is as the model's short-term memory. As it's thinking and generating text, it stores little calculations here so it doesn't have to do the same work over and over. And here's the key. Unlike the model weights, the size of this KV cache is completely dynamic. It changes based on the settings you choose.
So when you look at the whole picture, the model weights take up almost all the space. But it's that much smaller slice, the KV cache, that's the secret ingredient. It's a variable we can actually get our hands on and control to make a model fit our system. So let's see how this all comes together in a super straightforward calculation. We can take these two components we just talked about and use them to predict our total VRAM needs with incredible accuracy. Seriously? The whole process is just two simple steps. First, we just look at the fixed size of the model's weights. Easy. Second, we figure out the size of that variable KV cache, which is based on the parameters we're going to run it with. Which brings us to this incredibly simple formula. Your total VRAM needed is just the model's size plus the KV cache's size. That's it. It really is that direct. So let's put some real numbers on this. Say we have a model that has 17.7 gigabytes of weights, and based on our settings, we figure out that our KV cache is going to be about 1.6 gigabytes. We just add them together, our total VRAM requirement is going to be right around 19.3 gigabytes. Simple as that. Now, this is where things get really empowering. Because that KV cache size isn't set in stone, we can actually tune it. This means we can actively manage our VRAM usage and get these amazing models to run on hardware that we might have thought was way too small. And you have two main levers to pull to do this. The first one is context size. That's basically how much information, how many tokens, the model can hold in its short-term memory at one time. The second lever is KV cache precision. This is like setting the quality for those memories. You can use a high-fidelity format or a more compressed, lower-fidelity one. Just think of it like a high-res photo versus a low-res one. The low-res one is way smaller. The trade-off here is pretty clear, right? If you want maximum performance, you use a large context size and high precision, and that uses more VRAM. But if you need to save memory, you can shrink that context window and lower the precision, which can dramatically shrink the KV cache and your total memory footprint.
And here's what that looks like in the real world. Let's say a model with its default settings needs 11.1 gigabytes of VRAM. Well, just by tweaking the context size and switching the KV cache to a more efficient format, we can get that memory requirement all the way down to 9 gigs. And that could be the difference that lets it run on your GPU.
So the biggest thing to take away from all this is that you no longer have to guess. By understanding how GGUF works, and by knowing about the model weights and the KV cache, you can move from just hoping for the best to having a guaranteed outcome. You can calculate your needs precisely, and then tune your settings to fit your hardware. This knowledge completely changes the game for running AI locally. That uncertainty that holds people back is gone, and instead, you're empowered by calculation. You now have the control to really push the limits of what's possible on your own machine.